Hello, everyone. Welcome to Algebraic Topology in Physics, Part 4. Professor, could you take the conference? Thanks again for giving these wonderful lectures.
Okay, well, thank you again for inviting me. And yeah, let me begin by briefly reminding you what we arrived to last time. So we considered different realizations of gauge field for discrete P-1 form symmetry described by group G, which is assumed to be abelian. And so in principle, so the P equals 1 case is ordinary symmetry. And in this case, there is a version when G is non-abelian, but for simplicity, we still will assume that G is abelian. And so what were these? Yeah, roughly speaking, there are 3 different kind of way to realize this kind of. So far, it's just kind of background gauge field, which we later will make dynamic also. And so one kind of maybe the most, I don't know, natural in a sense is that understand this gauge field as a class in so again, the kind of as gauge invariant data of the field configuration given by the Pisca homology class of this our space-time M with coefficient in G. And so this A is it's realized by a piece cochain, which is by definition is it's element is a piece in the piece group of cochains in M, and meaning that it's a certain linear map from CP from the group of chains with coefficients in G to coefficient in Z to G. And then there was equivalent realization in terms of Poincare dual class in homology group. And this the chain representing this Poincare dual has interpretation, as we saw, as we argued, C has interpretation of network of topological charge operators. Which are kind of labeled by the elements of this group G, and that's why it's a chain with coefficients in G. More, it's a cycle, meaning that this kind of these defects in the network satisfy certain consistency condition in the junction, and yet there was third interpretation is that this class in cohomology can be understood as a homotopy class of a map from our space-time M to Ellenberg-MacLane space, KGP. So F is a map from M to a continuous map from M to this KGP, Ellenberg-MacLane space, and again, the kind of the gauge invariant data is this map is a class of this map up to homotopy. Okay, and then we also consider it kind of so this is just describes fields, and but to kind of to describe the dynamics of the field, we need to present some sort of action, and action on space-time M. We argue that it's natural to have it is the following form. So it's a kind of integral of Lm of B, where M has a meaning of Lagrangian, but here what we actually have Lm is element in this cohomology with coefficient in R mod 2 pi z. So the result is the element again is 2 pi R, sorry, R modulo 2 pi z. In particular, S is a kind of defined modular some sort of 2 pi integer shifts, but exponent IS is well defined without any ambiguity. And as a reminder, so what do you mean when we write this type of integrals is just by definition when we write, so in general, just a reminder, in general, if you write some sort of integral of h over sigma, where h is some class in, let's say, nth cohomology of some space X with coefficients in G, and it's represented by, say, let's say H tilde, whereas before H tilde is a cochain, which means it's a map from CNX from n chains to G, and so here sigma. So this integral is well defined if sigma represents a class in the n-dimensional cohomology with coefficients in Z. In particular, this means that the boundary of sigma is 0. And so by this integral, by definition, we mean just evaluation of this H tilde map on sigma. Okay. Yes. And this, okay, now we want to describe what is LM. So kind of given a B field, given field B, which is a P form with coefficient G, we need to define this Lagrange, which is will be D, is the elements of the D kind of the cohomology integer D. So this means that so, and we arrived at the last time we arrived at the conclusion that L to kind of, in order for this action to be local in a certain sense, this L should be a natural transformation. Between cohomology functors. And we reviewed what is the notion of natural transformation. It satisfies certain kind of neutrality conditions. And basically, when we, so this dot, we can plug any topological space there, in particular our space-time manifold. And we also, in principle, yeah, so we also observed that kind of using this Yoneda lemma result, one can show that this cohomology operation, sorry, this natural transformation, which is in particular in this case when it's a natural transformation between cohomology functors, this is what is called cohomology operation. So that cohomology operation are classified by this disk cohomology group of KGP with coefficients or 2 by Z. Okay, so yeah, this is a brief reminder what we had in the last lecture. Okay, let's see, maybe there are some questions. I don't see any questions, so I guess I will proceed with the new material.
Sorry, someone just asked, can you repeat why R mod 2 pi Z there?
Okay, so what we want, yeah, the goal that actually we want, so actually we want to define not action itself, but exponent of is divided by h. So because this is what we will have in the path integral, because we don't have actually, and of course we use a convention the h bar is equal to 1, which is convertible by rescaling our action. And so this means that we actually want to kind of define value in u1, because this is in u1. But defining value in u1 is the same as defining value of s in 2 pi, r divided by 2 pi z. So that's why we want this, we want this integral, which is, well, pairing between this cohomology class and this fundamental class of M to be valued in R model 2 pi z. And actually, one can see if one try just assume to R, so that R, one wouldn't get like one would lose a lot of interesting cases. And saying that it's well defined in R, it's actually too constraining, especially for this topological discrete gauge series. Any other questions? Well, Lagrangian is but here again the kind of the relation to some sort of Lagrangian form is kind of merely analogy. But I mean, why do we want? So in general, the point is that if you have something like this, and LM, suppose we consider LM to be some sort of this element of the this cohomology of M with some coefficients, I don't know, gamma, some group gamma. We want to ask what is it? What is this gamma? So this SM is this integral, which again by definition is just so this LM is given by some sort of represented by some class, let's say lambda. Lambda is this CD map from CD from d-dimensional chains in M with integer coefficients with to gamma. So this kind of this integral is just placeholder with this kind of result of evaluation of lambda on M. And M here, M is any D chain which covers completely our D-dimensional manifold. So this class of M is what is called in this cohomology is what is called fundamental class for our manifold M. So this the result of this relation is by definition is in gamma. So this, if you want S to be valid in some group, this L must be just by definition must be valid in the same group. Must be element in this cohomology with coefficients being this group. Any other questions? Okay, let's proceed to kind of with some what is the kind of basic examples of these cohomology operations. And first, let us know. So so we kind of first note that if you have a cohomology operations, for example, in general, we can consider kind of a cohomology operation H from HP1 with coefficients G1 to HP2 with coefficients G2, but then we can always consider composition of this cohomology operation. So we can go from HP2 to HP3 with some other coefficients. And of course, this composition is also a cohomology operation. So cohomology operation can be composed. And so in kind of very relatively simple cases, they will be composed using some very basic kind of cohomology operations. So what is this? So first, basic examples are the following. So examples of homology operations. So one kind of very almost trivial example is following. So suppose we have homomorphism from kind of group, let's say G to group H. So for homomorphism, let's say F, this gives us this can be used to obtain a homology operation from HP for any P G to HP H, and just by, so if you have some sort of if you have a class of cochain here, so we just compose this with A. So we kind of change we change the coefficient. We can change the coefficients according to some homomorphism between groups. Again, A here is a map from CP to G, and this will be a map from CP to H. Okay, so this is a kind of trivial example. One should be kept in mind. Second example is the following. So assume G is also a ring. So far G was an abelian group, but let's assume that this it's also a ring. So kind of, well, in the ring, well, we assume it's a commutative. So the plus operation in the ring will be our group operation, and the but we also add a product, new structure. So example, basic example is G, for example, is a cyclic group of order n. So this can be understood as a group of integers modulo n, and this has natural multiplication. So we can multiply integers and consider the result modulo n. Is a ring. And then we can define what is called the cup product. So it's a map from H P. So let us fix our space M, H, let's say P1 with coefficients in G times H P2 with coefficients in G to, so this is usually noted like this. That's why it's called cup, to H P1 plus P2 G. Okay, you can so the well, this is okay. In this way, it's not quite a cohomology operation, but one can construct because it's it's not quite of this form, but one will be able to use it. Well, as you see, one can use this operation to actually construct cohomological operations. So how is this defined? So suppose we have this class of some class A1 and some class A2, and this pair must go to some class of A. So what is this? How this A is defined? So again, so A1 and 2. So they were C. Okay, let me write it like this. AI is a map from CPI and Z to G. And now we want to define A, which is will be a map from CP1 plus P2 M to G. And so these well, the chains are generated by the singular simplices, so maps from simplices to our space M. So to define this A, we need to define the value on arbitrary singular simplex alpha. So singular simplex, this is a map from simplex to M. And this value is defined as follows. So we take A1 and we consider its value on certain simplex delta P1 and a copy of delta P1 and A2 on delta P2, where delta Pi are embedded in a certain way into this larger P1 plus P2 dimensional simplex. So this is okay, let me explain this. So the embedded so the so included in the way that they have only one common vertex. And so, for example, if say P1 equals 1 and P2 equals 2, so the sum is 3. So we have a three-dimensional simplex, which is a tetrahedron. And then, so we embed kind of, so they're always embedded as some of the natural subsimplices. So say kind of the vertices, they embedded in the way that the vertices, set of vertices coincide with the set of vertices of original simplex. So this will be an example where we have this delta 2, and this will be delta 1. And okay, and yeah, this is basically the definition. Then we define this the cochain this way, and one can check that it's if A1 and A2 were closed, then so they represent, because they represented some classes in cohomology, this will imply that A will be closed, so it will represent a certain class in cohomology. Sorry, what I wrote is not super precise. So let me. So we consider, of course. So what I mean here is we consider restriction of alpha on this. So we take a restriction of alpha, and this restriction will give us well, map from a low dimensional simplex to M, and then we evaluate these cochains A1 and A2 on these restrictions. Any questions? Is there some questions? Can you please recall why does the classification involve the cohomology of Algebraic space. So okay, this we're not really going to use this in later. So, but I just wanted to mention it because it often appears in the literature. So the this is implied by this general Uneda lemma, which I'm not. So if you're interested, you can look up. But the basic argument, the basically correspondence works. So let me remind you how basically the correspondence works. So we have a. So first, yes, there is a general statement that h n of x with coefficient g as a set, at least as a set, I mean, one can talk about the group structure, but let's not worry about this for a moment, is the same as a set of homotopy classes from x to k gn. And well, this I have not really explained it, but that's a fact. And this falls from the fact of how these k's are defined. So they have a homotopy group concentrated in degree n. And then if we assume this, so we want to, for example, for cohomology operation, this is a more general statement. So for cohomology operation H, let's say P G to H P prime G prime, this can be understood as this type of. So we are well, let's consider particular space M, and which can be arbitrary. So we want so suppose we have some element here B, and B again can be understood as well, let me write it this way. Let's say B tilde, which is a map from, yeah, using the correspondence maps. This can be understood as a class of map B tilde from M to KG. And then, so suppose we have now F, a map from KGP to KG prime P prime. So we can then use this map and compose it with this B tilde to get B tilde prime. So it's a composition. So F, there is no prime here, just F. And then this the class of B tilde, using again this correspondence above, the class of B tilde, this map B tilde prime comes out as a class in this cohomology HP prime with coefficient G prime, right? So this, so if you have this map from between Algebraic McLean spaces, this define us. This gives us this natural transformation, this cohomology operation. And we can check. It's easy to check that all these properties of natural transformation will be satisfied. But now F, so we can see the homotopy, and the result will only depend on the homotopy class of F, because basically everything is considered up to homotopy. But the homotopy class itself is a class of homotopy, is the element of the set of homotopy classes from KG P to KG prime P prime. Right? And now we use again this relation between homotopy classes and cohomology classes, and this is H P prime of KGP. So we basically use this as our X, HKGP with coefficients in G. So that's a brief reminder of how this correspondence works. Okay. But okay, let's go back to this. Okay, so we consider cup product. So this so nice things about this cup product is this makes so we can consider the sum of all, again, so there is for G ring. So we consider the sum of all cohomology, the direct sum, which is denoted by this H star usually. And so it makes it into a graded ring. And it's graded commutative, meaning that A cup B is equal to -1 times degree of A, degree of B, B cup A. And degree is this index of the cohomology. Here we mean that A is the element of degree A mg, and the same is for B. And yeah, it's a kind of now we have this gives additional structure on these cohomology groups, and it could be that actually that could be the examples of topological spaces, even just manifolds, which have the same cohomology as a groups, but cohomology as a ring is different. And what is the okay? Maybe it's also worth mentioning what is the interpretation in terms of this cup product in terms of Poincare duality. What's this? So suppose we have cup product of B1 and B2 equals to B, and this is let's say Poincare dual to some class of some cycle C, and this is a class of some cycle C2, and this is a class of some cycle C. And so roughly it works like this. So we have some sort of chain C1, and then we have a chain C2. So this was C1 was D minus. So now we consider this in a manifold of dimension D. So this chain is D minus P1 dimensional, and this is D minus P2 dimensional. And so the intersection is generically will be of dimension d minus p1 minus p2, because when you intersect some kind of submanifolds, the codimensions add up, and so it's very good in a smooth manifold. The cohomology classes can be always represented by chains which consist of the singular simplices which are actually embedded in the manifold. And this is this intersection will be our chain C. But of course, we also have to remember the coefficients. So if this C1 has coefficient n1, this C2 has coefficients n2, so Ni is in G. This will have a coefficient n1 times n2 in G, where this product is a ring structure product. Questions? Okay, and so maybe give some examples of rings, examples of cohomology rings. So one of the kind of very important examples is a cohomology ring of CPN, so n's projective space with coefficients in Z. And so this is as a ring. So basically a ring of polynomials in some variable x with integer coefficients modulo xn plus 1. So we just kind of we divide. So this whenever we have n plus 1, n plus first power of x, we say it's 0. And well, here the degree of x is 2. So we have basically a single generator in each degree, which is a power, the corresponding power of this x. And the other important example is the cohomology ring of RPN with Z2 coefficients. This is again a polynomial ring with Z2 coefficients modulo xn plus 1 again, and here the degree of x is 1. We have a single Z2 generator in each degree. So, for example, how can we construct a cohomology operation from a ring structure?
Sorry, someone asked in the chat box a clarification question.
Do you mean by this notation 1 plus x? Well, not really. Well, by this notation, I mean so they are kind of generic. So how does the element here looks like? General element in this ring looks like this: sum of let's say ai xi, where I goes from 1 to n, and ii is an integer. And then the ring structure is given by multiplying these kind of polynomials with integer coefficients and setting xn plus 1 to 0. So for example, if you have a let's say cohomology ring of CP1 is just z of x divided by x squared. So we can have something like 1 plus 2x as an element here. And for example of multiplication is, let's say, 1 plus 2x. We can multiply to 3 plus, I don't know, x. And the way it works is 3 plus 6x, sorry, 7x, yes, plus, yeah. Well, in principle, one can consider they're kind of 2x squared, but this is a 0. So all z for and others, yeah, that's correct, yes. Sorry, no, yeah, yes, that's correct, yes, that's correct. And the generator is this x x to the n. Yes. And similarly for RPN with the two coefficients. So here for each, yeah, here in this case, this is HK RPN is equal to Z2 is equal to Z2 for K from 0 to N and 0 otherwise. You're just writing kind of the result in this way. We immediately give a ring structure. It's not just a group structure, not just group structure in each degree. It tells us what is the ring structure. Okay, so how can we use, for example, cohomology operation from ring structure? So let's say we have something like where one basic example, if you have a h1 of x, we can use something like this, you know, one of the basic examples. G to construct a homology operation like this by taking some B here and taking it to B cup B. And one can verify that it's indeed a cohomology. Or we can have, for example, we can have something like H1, let's say, of G times like 2 copies of G, which is the same as H1 G times H1 G, and then we can use it as a cup product to go to H2 H2 of G, and this composing this gives us this cohomology operation. Okay, and okay, so another important basic operation is the what is called Bockstein operation. And so how it's constructed, so consider short exact sequence of abelian groups. K goes to H to G to 0. Suppose we have some maps R and J. And if we have this exact sequence, we can construct a cohomology operation which works as follows. So from the piece cohomology with coefficient G, we can go to the piece P plus first cohomology with coefficients in K. And the way it works is the following. So suppose this is given by some class of A, and so we will take it to, so this Bockstein applied to B, which should be a class of well, let me call it A prime. So so we need to say how A prime is determined by A. So A is by definition is map from CP to G. If I don't write, yeah, with CP here is with integer coefficients, and A prime must be a map from CP1 to K. So A prime is determined by essentially solving the following system of operations. So what we do is the following. So we take our cochain A. So it's a cochain with coefficient in G, and then we use this the J to lift it to let's say A double prime. So A double prime now will be a map from CP to H. And one can argue this is always possible. Well, this is basically because J is, by construction, J is surjective. And then we apply co-boundary. The second equation in the system is that we apply co-boundary to A double prime, which we lifted, which is by definition is this composition. And we want to find A prime now, such that if we apply this map AI, which takes us from K to H, we get this co-boundary applied to A prime. And well, solution always exists because the solution exists because if we, so what, I mean, why can we find such A prime? Because if we apply J to this co-boundary of A prime, we get we can exchange this co-boundary with J, and this will be but J of, by construction, J of A double prime is A, and the co-boundary of A is 0 because A represented a class in cohomology. This means that this means that this co-boundary of A double prime is in the kernel, valid in the kernel of J. But this means it's valid because of the exactness of the sequence, which we have. This means it's valid in the image of I, and then this means that we can find this A prime. So roughly it works like this. Okay. And of course, this can be a bit counterintuitive, but okay, this question maybe. Okay, let me, sorry, there's some questions. Let me see. But with this concretized intersection, since we are considering classes of chains, how do I consider the intersection? Is it like minimal intersection? Oh. So here, yeah, was more like a geometric interpretation. I mean, actually, the way to define intersection is to define as a cup product in cohomology. So this is, but morally, I mean, if you have if you represent everything by some sort of if you arrange everything in this way, that intersection is nice, everything is transversal, then you can do this. So in particular, yeah, if you imagine that these chains are represented by some smooth submanifolds and their intersection is such that it's also smooth submanifold, then it works in this way. Yeah, but well, there should be so it's not we don't need it to be minimal in the sense like it can be any kind of chain which obtained on this in the intersection. So any chain which supported on the intersection, but one can argue that okay, the chain you can get different chains, but like if you choose start with different position, you will get different chains, but the resulting homology class will always be the same. So okay, you can see the minimum, but it's not necessary. Again, yeah. Because we can see that it's not because it's not just a kind of intersection as a kind of subspace. It's an intersection. We also have the coefficients, right, which are given by this multiplication. Okay, another question: is this the connecting homomorphism which you said once that appears in gauge? Yeah, this basically, yeah, what kind of this is a part of this general story where we have if you have a short exact sequence of complexes, this induces long exact sequence of homology groups, and then this beta is in this particular case is what is called connecting homomorphism. Okay. Yeah, maybe just to argue about this minimal, so we can consider something, for example, locally, which looks intersection like this, or you can do something like wiggle it a little bit, and it will be like this. But here, this the intersection will be basically so it's a kind of intersection of like pair of one chain. So this is will be. It's important that we take into account, of course, the orientation, right? Everything is oriented. And so this will give us like suppose we have just coefficients integer numbers. So this is 1 and this is also 1. All coefficients are 1, and this will result the intersection will be 0 chain with well +1 here, but in this example this will be 0 chain where we have +1 here, -1 here, and +1 here. But kind of they have so intersection they give the same class in H0. Well, here, yeah, this intersection number, if it's if it is kind of if the result is of dimension 0, like in this picture, yes, the intersection number is invariant. Yes, it only depends on the homology classes of these chains that we started with. So on homology classes, yeah. But in general, the intersection is not a number. It's a new chain. Okay, so okay, let me also give kind of a Poincare dual interpretation, which is maybe more geometric interpretation of this Bockstein operation. So Bockstein operation in terms of Poincare dual. So okay, so we had so we have so operation works like this: B goes to beta B, and this let's say this will be Poincare dual to some class of some C, where C is so B was in HP, and this is in 8D minus P. So C is a D minus P cycle. And so as we saw already by this time, so multiple times, this can be kind of understood as, so formally it's a linear combination of singular simplices. So it's a kind of network, can be sort of this network of simplices inside our manifold, and they're colored by elements of the group. And so we have some sort of generically there will be, so if these are D minus P dimensional, generically they will have some kind of junctions of dimension D minus P minus 1. So like this is sort of two-dimensional surfaces, and they have the junctions, which is like one-dimensional line locally. And so what we do is the following. So we have this N and G, and then we have this surjective map J from H, and we can lift. So the first thing we do is we lift an ice to n I tildes in this group H, so meaning this J and I tilde is in H. So before we had, since it was a cycle, so C is a cycle, we have a condition that okay, with proper signs, according, well, is 0, right? So because the boundary must be 0, so this kind of conservation law at the junction. But this means that we will have so let me choose orientation that all signs, for example, all signs are pluses. Not to worry about it. But this will imply that J, so J of this N1 tilde plus N2 tilde, 3 tilde is 0, but these lifts themselves, they don't necessarily obey this conservation law at the junction. So this is in general non-zero. So again, yeah, this is J of N1 tilde, this is J N2 tilde, and this is J tilde. So we leave these coefficients to H, and but we know that J of M is 0, and since we have this exact sequence, the M is I of some, let's say, L. And we have, and this L, because I is injective, L is uniquely determined by M. So basically, so this okay, now we want to define so it's kind of consider now D minus P minus 1 dimensional cycle consisting of these junctions. Let's say cycle C tilde junctions, and color it by this L, which is it's locally at each kind of junction we assign this label L in K. well, this gives us so this gives us something which represents a class in d minus p minus 1 dimensional homology with coefficients now in K, and this is a Poincare dual to H p plus 1 m with coefficient in K. And if one compare it with previous definition, one can see that this is must be Poincare, and the way Poincare duality works, one can see that this is a Poincare dual to the Bockstein operation applied to this. Questions? Is this exactly connecting homomorphism homology? Let's see. Probably yes, but let me be more careful. So for homology, so let's see. So for homology groups, we have the following. So we have D minus. Yeah, I'm not sure if I should spend time on this, but anyway. So we consider for homology groups, we have HD. Let's see, minus PM K HD minus P MG HD minus P M. So how is it? No, it's not. How? What was the sequence? K goes to H to G. So and then we go to HD minus P minus 1 MK. Yeah, it works like this. Yeah, so this is the connected map. Okay. Any other questions? Okay, so let me make the following remark. So kind of in the analogy, we can already use this step. In the analogy, HPMG with some sort of differential forms on M. So we already had a notion of kind of this integration, which is analogous to the usual integration. But now we have a cup product, which is actually analogous to a wedge product. And one can see that when we have this cohomology with R coefficients, with real coefficients, it's essentially the same. And this Bockstein is in a sense analogous to exterior derivative. So things become particularly nice if, let's say, for G, let's say ZP, some cyclic group, which is again, so it's also a ring. We have this beta is a derivation in the following sense. So beta, apply beta to this like a cup product of A and B. this is has this derivation rule plus let's see, -1 to the degree a cup beta. Okay, and another remark for G equals Z2, and let's say B, when B is element of H1, M condition Z2, we have this nice property that the Box-Chain of B is actually the same as B cup B. So in this case, essentially, well, using also this derivation property, the action of Box-Chain reduces to just cup product. Okay, and then let me make the following statement. So cohomology. So okay, this was this basic cohomology operation, and now one can observe the following. So cohomology operations for a finite abelian G. Well, from H1 G to HD of well, we're interested for our application to this gauge theory, interested to this cohomology operation. Are basically are compositions of the basic operations above. I don't prove this or explain it in any way, but this is a fact. One can't argue. Okay, so consider some examples. So let's G will be Zn, some cyclic group, our gauge group is now, and P equals 1. So we have a usual zero form symmetry. Gauge, so B is element of H1, M with coefficient Zn. Let's say what all possible. Let me list what all possible actions in can you have in some small dimension. So for dimension, when dimension is S, you only one can only have the following basically, where we have S is let's say integral. Well, let's write it in this way: 2 pi m divided by n kb. So here we need we basically use so this we use a kind of this inclusion of Zn into 2 pi, sorry, r divided by 2 pi z. So kind of as the last cohomology operation, we use this inclusion, kind of this homomorphism between coefficients, which works in this way. So well, x goes to 2 pi x divided by n. So kind of this works as a multiplication by 2 pi n. And here k is some element in Zn. So we can multiply, of course, we can multiply if you have a, so in general for G ring, this H star G is a G model, naturally, because we can multiply, well, this, again, it's represented by functions in G, so we can multiply, since G is a ring, we can multiply by the elements in G. This K is just started by multiplication. And so, okay, so this, in order, well, this is a, maybe I should make more. So this is the element of H1 of M with coefficient Zn. This is a gain, which is multiplied by element of this ring Zn. This is still this element. And this finally will multiply by 2 pi divided by n. This gives us the element of H1 of M with coefficients R mod 2 pi Z. And it's basically everything. Yeah, there's only a possibility we can have in dimension 1. So in dimension 2, one can argue that the only possibility is actually identically 0. Okay, naively, one can write something. Okay, one can try to do something like 2 pi n b cap b, but one can argue this is always 0. Or one can write something like 2 pi n Bockstein of b, for if you use Bockstein for this sequence Zn squared Zn. Yeah, by the way, here, of course, when I, yeah, maybe I didn't specify this, but when I talk about this derivation, yeah, this is a Bockstein for this specific sequence. So it gives us, it preserves the coefficient ring. Let's take this one, and the same thing here, Z2, Z4, Z2. So I should have mentioned this. And this is, so this will be actually 0. And for example, for d equals 3, we can again have something non-trivial. Okay, S is integral of 2 pi n. So again, this is just coefficients. This is just to go from Zn to 2 pi r. So r divided by 2 pi z. And then we consider b cap Bockstein b. So this is element in H3. Maybe I give examples. Let's see. Yeah, maybe. So if you have a product of cyclic groups, things become a bit more involved. So G is Zn times Zn, and well, basically we can see, okay, our field is in H1. Let's still consider P equals 1 case. H1 of M is coefficient Zn times Zn, but the product for product of coefficient is just the same as the product of the cohomology groups. And we can say that B is this pair B1 and B2, where B1 is in the first factor and B2 is in the second factor. And then, for example, for D equals 2, well, for D equals 1, we just can have, yeah, for D equals 1, we can have now two kind of, well, basically linear combination of what we had before, K1 B1 plus K2 B2, where Kr is in Zn. And for D equals 2, before we had just 0, and now we can have something non-trivial. We can consider B1 cap B2 with some coefficient K. And for D equals 3, we can consider the following combination of K. So again, Ki will be in these coefficients in the end. You can see K1 be B1 cup Bochstein of B1 plus K2 B2 cup Bochstein of B2 plus K3, and for mixed term B1 cup B2. And so we don't need to consider B2 cup beta of B1. This is because this beta is a derivation, so it's the same as minus B2 cup beta B1. Actually, no, without minus. Simply without minus. Questions? So are we supposed to do some break or not?
It's up to you. If you think you want to do a break, then we can certainly break for maybe 5-10 minutes.
Okay, maybe we can do a 5 minutes pause. Continue. So yeah, now we have everything we need, and so more or less to define what kind of the analog of path integral for these discrete gauge series. So we want some sort of path integral, which is analog of something you ordinarily see in a quantum field theory, quantum mechanics, some sort of you integrate over some fields on our defined on our space-time manifolds of x with some measure, and you integrate this exponent of I times the action. So in particular, if you don't have any insertions, we can consider this kind of path integral with no insertions. This is what is usually called partition function. So in our case, let's consider this partition function and assume that M is closed, oriented, and so we need to integrate over all possible fields, and here it will be just a sum over the fields, and we know the fields valued in piece homology with coefficient G of exp M B. And so in principle, there could be some normalization factor, and we have to figure this out in order to actually calculate some values, right, as a partition function. And so this normalization factor, okay, let me so kind of write the answer what this normalization factor is. So the answer is the following. So we consider we divide by the size of the number of elements of P minus first homology groups, and we multiply by H P minus to mg. Then we divide by H P minus 3 mg size, and so on until we reach H0. So in particular, for P equals 1, kind of the gauge usual zero form symmetry, this normalization factor is just 1 over H0 mg, and this is the same as 1 over size of G to the number of connected components. If M is connected, then it's just 1 over G, 1 over size of the G. Okay, how do we? Okay, let me give you some sort of not very kind of precise argument, kind of physics argument. What is a physics argument? So if you use using non-gauge invariant field, which is kind of A will be a chain, co-chain with coefficient G, so that B is a class. We want a class of B to be a class of this A. We can write, we should be able to write this partition function in the following. So sum of kind of maybe in certain this amount exp I as write S tilde M of M. So this is a kind of lift of cohomology operation to the cochains. And this is always possible because the way we always defined this cochain, this cohomology operation actually using cochains. And but we actually want this A to be so if you just say that A is cochain, that is not going to represent any cohomology class. So we need condition for this to be closed, and this can be implemented as some sort of using Lagrangian multiplier. So this is graph lambda. So we sum node over A, which is CP mg, and this is some sort of Lagrangian multiplier. And so lambda is in CD p minus 1. Well, in order for this to be valued again in 2 pi, sorry, r divided by 2 pi z, we need lambda to be cochain with coefficients in form g to r divided 2 pi z. And here we want, so usually when we have a kind of we want to divide by kind of the volume of well, the size of the gauge of the group of gauge transformations. So this Lagrangian multiplier just makes us we can actually get rid of it, kind of integrate it out in the sense integrate lambda out. And just sum, so we have a sum of sorry, let me write this in the, so here will be in a kernel of delta acting on CP exp and so what is this group? So what is the gauge transformation? So gauge transformations, well, A goes to A plus delta of A tilde, where A tilde is a P minus 1 chain. But of course, there are also kind of gauge transformations. In general, there are also gauge transformations of gauge transformations. We can change A tilde also by itself by co-boundary of some A double tilde. And this is not going to change the gauge transformation itself because delta square is this co-boundary squared is 0. And here A tilde is in C P minus 2 mg. And so on. There will be a kind of gauge transformations of gauge transformation of gauge transformation. And so actually, so this in this kind of realization, when we use this A kind of when our field is a cochain, this kind of volume gauge summation is kind of informally can be written as the kind of the size of HP1 of M with G. This is a kind of gauge transformation, but we overcount it. Here we are overcounting gauge transformation. So we need to divide by the volume, this itself to divide by the volume of gauge transformations of gauge transformation. But here again, we still overcount. So we can need to divide it by this. And so on. Okay, and but now we so the next step is we reduce it. We kind of do a gauge fixing, in a sense. And so we want to write it as sum over just. So basically, what we mean, we fix a representative A or B. And here we will sum over B in just as the variant, we sum over just B of HP. So when we fix okay, yes. So this okay, just a second. Okay, so our so we know that so what is it when we fix a representative, we only need to quotient, so this A tilde. So what is it now? We fix A. So what kind of A tilde? This gives us conditions that A tilde cannot change. Then we can only allow the gauge transformation which do not change A. So this means that now after gauge fixing, so this A tilde must be in the kernel of delta acting on, well, let me write it as just delta P minus 1, where we use this notation as before. So we have CP, delta P acting on CP, it goes to CP plus 1, then we go to delta P plus 1, so on. And here we have delta P minus 1, CP minus 1, and so on. And so this means that we don't need to divide by all CP minus 1 here, but we only need to divide instead by just kernel of delta P minus 1, the size of the kernel minus 1, but the rest will be the same. So it will be CP minus. Okay, let me write it in black. Well, let me don't indicate this suppress the dependence on M and G, and there will be a size of CP minus 3, and there will be size of CP minus 4, and so on. Okay, but now we can use this the kind of the fundamental theorem of kind of group theory, which tells us this. We can write kind of the size of the group is a product of the sizes of these. If we have some map defined some homomorphism defined on this group. This is the size of the group is a product of the size of the kernel of this map and the image of this map. And the same also we can write for CP3. Okay, and so on. And let's plug it into this normalization. So this is what should be our normalization coefficient, right? Because here we already did gauge fixing. So this is equal to the size of the kernel delta p minus 1 divided by, so in the numerator now we have a kernel. So let me write it in this order. Image delta p minus 2 times kernel 2. This was came from this thing. And then we continue. So the kernel of delta pi minus 3. Okay, let me, too busy to write in this order, image delta times kernel. And then we, and here image delta pi minus 4 times kernel delta pi minus 4, and so on. And now let's see. So we know that the cohomology group HP is a kernel of delta p divided by the image of the delta p minus 1. So in particular, the size of, yeah, we can, the same true for the size. So the size is the ratio of the sizes of this group. And we see exactly, so this is now, this ratio is what is, so we can, yeah, is 1 over h p minus 1. Now this ratio is size of hp minus 2. This ratio is the size of h 1 over size of h p minus 3, and so on. So this shows that this that we indeed have this formula for normalization coefficient. So at the very end, so what is this? So we have now we have a very precise expression for partition function. It's h p minus 1 m g h p minus 2 m g p minus 3 m g. And then there's some b h p. Questions? Okay, let's do a particular, yeah, let's consider some simple examples of calculation of partition function. So let's consider group to be Z2. And let's say D equals, sorry, what? B. Okay, V equals 3, and S will be well, just pi integral A cup A cup A. Well, okay, here maybe I use B as before. I use B cup B cup B. And for example, if we, P equals 1, of course, here. So B is H1 C2. Now let's consider a few different manifolds. So let's M is a 3-sphere. Well, for 3-sphere, the cohomology group is identically 0, so there is no sum, right? There are only a single element of the sum, then B equals 0. So this Z of S3 is just 1 over, well, we still have this normalization factor, which is here S3 with coefficient with Z2 coefficients times, well, the sum, well, the action is identically 0, sum of 1, and there is a single element, well, there's a single element in the sum, which is 1. And this is 1/2. And another example is M is RP3. And so, as we saw earlier, the cohomology ring of HP3 is this Z2 of, let's say, X. So in particular, H1 of RP3. Z2 is, well, generated by this X. Sorry, over Z2. So there are two choices. So B can be either 0 or B can be X. So there are two gauge field configurations. Well, up to gauge transformations, which we need to sum over. So the pressure function is 1 over this normalization factor, which is 1 over 2, as we figured out, plus X per, well, e to the I0. When B is 0, S, of course, is 0 automatically, and then there will be, since we have X cup X cup X, well, this is, sorry, here X4, it should be X4. It's like this X3, and, well, H3 is generated by this X cube. So X cube is a Poincare dual to, sorry, what I want to say that is yeah, so this, well, since the generator in the top degree cohomology is evaluates on the fundamental class, evaluates to basically to 1. Well, here is maybe RP3. So we have pi I pi, which is -1, and this is 1. So we have 0. And so this is the Z of R3. Maybe another example is T3. So here for the cohomology ring of T3, these two coefficients can be suited as okay, polynomials in x, y, z, and they're divided by relations. Yeah, the relations that x square equals 0, y square equals 0, and z square. Sorry, no. Yeah, that's correct. Yes, this is 0. There's a question. Sorry, M is a slice of space-time here, or the space-time? Yes, it's space-time. Yeah, M is the full space-time. And yeah, we'll talk about kind of spatial slice, which will be d minus one dimensional a bit later. And so this kind of yeah, the first cohomology in particular is the two coefficients is generated over Z2 by this x, y, z. This is Z2 cube. And well, we can understand how geometrically one can understand them the following. So we can understand T3 as a sort of cube where we kind of identify opposite sides, and so this kind of x, y, z are Poincare dual to T2s naturally embedded in T3. So this is kind of x, y, z, this three orthogonal to tori. Which represent this story. So this give classes in H2 T3 with coefficients Z2. And yeah, this the ring structure can be easily figured out by considering these intersections. Particularly, the squares are 0, meaning that there's no self-intersection. One can easily see it because one can kind of work to kind of calculate intersection. We take a kind of the chain and the copy itself, but we kind of a little bit deform this. But here we can take kind of this, for example, for y, you can take this torus and we can have its copy a little bit shifted. And when we shift it, it's not going to intersect the original copy. That's why self-intersections are 0. And this means that the squares of these cohomology classes are 0. Okay, and so there so in particular so this implies since the squares, so the general, so B, so kind of general field configuration is can be understood as this thing. So kind of alpha x plus beta y plus gamma z. This is NH1, and where alpha, beta, gamma are the two coefficients. And well, because we have all these squares are 0, this for general B, this is also with the 0. In particular, S is which is basically pi integral of B cube. It will also be identically 0. And so the normalization will be 1/2, and we have to sum over 8 different, 2 to the cube field configurations, right? And the result is 4. Yes. So here we saw that on 3 torus, the result is integer. And actually, this is not this kind of expected because so in general, we can consider space-time M of the form And so it's a d-dimensional spacetime of the form where it's a product of d minus one dimensional kind of space. And this is a kind of time direction, which is compactified. And in general, we know that if you consider partition function of quantum field theory on this type of spacetime, where we have kind of the time direction is circular, this has interpretation of what is kind of originally probably was called a partition function, in particular in statistical physics interpretation. So this is given by the trace of EIHT, where so it's trace over H, where H is a Hilbert space on of the quantum theory on this ND minus one. So which means we can quantize the theory on this particular space-time, which is the product of ND minus one times R, which is the time direction. And well, H is the kind of Hamiltonian acting on this Hilbert space, and T is the size of the time circle. But here, I mean, you have a topological theory, right? Nothing depends on metric. Here, nothing depends on metric. In particular, it should be independent of T. So this means in particular, the Hamiltonian is zero. So it's kind of, you could say, okay, it's something trivial, but it's actually not. Even if Hamiltonian is zero, the kind of quantum field theory can be non-trivial in a certain sense, as we'll see in more detail a bit later. So basically, then this reduces to just trace of one over the Hilbert space, and this is so let me emphasize the Hilbert space on this manifold n, and this is well, trace of one is the dimension, and this is basically all states are ground in our theory, and actually in general topological quantum field theory, where there is no dependence on metric. All states are ground states, but they might be still non-trivial kind of. One of the non-trivial data is a ground state degeneracy on a given space-time. So this is a ground state. In particular, we saw that for this theory, which we consider, there was four ground states. And let me consider as an exercise. Let me propose the following exercise for the homework. Let's say that consider theory of Z2 times Z2 times Z2 gauge theory. So it's the usual. So B will be in this is G in H1 of MG for dimension 3, and two cases. I'll consider two cases. Well, let's say case 1 is S is 0, and the case, well, and the second case is S equal to, so here, again, so G is a product of this group. So this G is B can be understood as HMZ2 cube. So the three copies, so B can be understood as, let's say, B1, the triple B1, B2, B3, where each BI is just Z2 gauge field. Okay, Z2 cube gauge field can be understood as a triple of topology is triple of Z2 gauge field. And in the second case, we take S to be pi integral of B1 cup, B2 cup, B3. And the question is calculate in both these cases, calculate a ground state degeneracy on two torus. And I think with, sorry, let me have yes, the next step, okay, yeah, I have to finish. So the next step would be considering some sort of describing some observables in this year, and then I would talk a bit about general notion of topological quantum field series, and in particular, what is kind of physical motivation of considering this topological quantum field series. And then I will mention about something, how this actual classification of this gauge series should be a bit modified, should be corrected. And the actual classification is given not by these cohomology operations, but by some sort of cobordisms. Yeah, but this will be next. I think this will be next time. Okay, so yeah, I stop here, but maybe there's some questions.
Thanks, Professor Pavel Putrov, giving this lecture. And there are several questions in the chat box.
So curious question, do you know why when the time direction is compactified, like S1, is typically used in statistical physics? Well, yeah, usually we also go kind of yeah, kind of in the actual like Lorentzian space-time, it's not good to have like circular time-like circles. So we usually do this actually compactification when we do the Wick rotation, and then actually like after Wick rotation. Sorry, Wick. Second. So after Wick rotation, well, which roughly T goes to IT. So we get this Z of N times this one is a trace of E minus HT. And this is, well, if the Hamiltonian is non-trivial, this is something like sum of states E minus En T. And this is like thermal, yeah, this has interpretation actually. T has now interpretation of something like 1 over temperature, right? And this gives a sort of partition function of like this exponents is how you get the distribution of states in the sort of thermal equilibrium. And so this kind of this is some sort of probability for state. And that's why it's in a sense more naturally has this statistical physics interpretation. Yeah, so yeah, this is this is quite a roll course. What certainly this allows kind of time traveling connect. So actually, yes, this is not this is not a physical like space-time. Lorentzian space, so actually physical space-time should be a Lorentzian, but there will be issues of putting Lorentzian metric here and well, Anyway, yeah, this is usually this is understood after doing this weak rotation with the Euclidean space.